All right, here goes. I apologize for the poor voice and everything, but we're going to go ahead and do the Chapter 3 lecture. I didn't get Mike Rowe to do a voiceover, obviously, so let's give her a try. All right, bonding. Bonding is essentially a stable arrangement of atoms, okay? Two or more atoms into a stable arrangement. Now, how this happens, we classify based on some models that we've come up with, okay? I want you to understand that really we don't know how bonding works, okay? We have these models that we use to try to explain how bonding works. So, what we see is that elements tend to gain, lose, or share electrons in order to reach a noble gas electron configuration, okay? So that leads to two different types of bondings. When we gain or lose electrons, we end up with ionic species, ions, charged particles. That's the result of the transfer of electrons from one element to another, okay? Covalent bonds, this is an overlap of electron density between two atoms, so the sharing of electrons between two atoms. So, ionic bonding, we generally say, forms when we have a metal with a nonmetal, okay? Metals, remember, are on the left side of the periodic table, nonmetals are on the right. So if I take a chunk of sodium metal and some chlorine gas and I put them together, I get this beautiful exothermic reaction. It heats up, it lights up, it's gorgeous. And what I end up with is sodium chloride, salt, okay? Sodium chloride consists of the sodium ion and the chloride ion. Now what happened was sodium metal here has 11 electrons because it's got 11 protons. Chlorine here has 17 electrons because it has 17 protons. Sodium will lose 1 electron to give it 10 electrons, which means it's lost a unit of negative charge. Therefore, it's got more protons than it does electrons. So it's going to be a positive charge. That electron is added to the chlorine. So plus 1 electron there. Now I've got 18 electrons. I've got one more unit of negative charge than I do positive charge. Therefore, it's a negatively charged ion. If you take a look at the periodic table, what neutral atom has 10 electrons? What neutral atom has 18 electrons? Neon and argon, the noble gas electron configurations. Now, covalent bonds are formed when two nonmetals combine, or when a metalloid bonds to a nonmetal. And what we get from that is a molecule. It's a discrete group of atoms that share electrons. Okay, that's different than the ionic bond. The ionic bond leaves us with a crystal, okay? And as you saw in that previous slide, there was actually this lattice of positive and negatives all put together. But a molecule is a single discrete unit. So if I take two hydrogen atoms and I bring them close enough together, they are going to share electrons in a covalent bond. And I get a hydrogen molecule. All right, ions are charged species in which the number of protons and electrons in an atom is unequal. Okay, as we saw with the sodium chloride example, sodium lost an electron and it had an unequal number of electrons and protons. And so that is what an ion is, a charged particle that has an uneven number of electrons and protons. If you have more protons than electrons, you're a cation. That is a positively charged species. If you have more electrons than you do protons, you are an anion. That is a negatively charged species. And ionic compounds consist of those oppositely charged ions. So, let's take a look at the electron configuration from the sodium atom. Sodium atom has a 1s2, 2s2, 2p6, 3s1 electron configuration, which means its valence shell is that 3s electron. If it loses that one electron, now it has 1s2, 2s2, 2p6 electron configuration, which is the same as neon. Remember, 8 electrons in the outer shell, the octet rule. that 8 electrons in the outer shell is a particularly stable configuration for atoms. So it has more protons than it does electron. One more proton than electron, a positive 1 charge. Let's take a look at magnesium. The magnesium atom has a 1s2, 2s2, 2p6, 3s2 with 2 electrons in its valence shell. If it loses 1 electron, it's only going to be a +1. But if it loses 2, now it's going to get 8 electrons in its valence shell. So losing 2 electrons is going to give me 10 electrons with 12 protons. So that's a net positive 2 charge. Again, this is 10 electrons. This is the same as the neon noble gas configuration. So you can lose multiple electrons to form cations. Now you do this until you get a completely filled valence shell. So as I said, if you lose electrons, you get a cation. If you gain electrons, you can gain 1, 2, 3, or more electrons to form an anion. And you do that until you get that completely filled outer shell of electrons. This leads to the octet rule. A main group element is especially stable when it possesses 8 electrons in its outer shell. Octet equals 8 valence electrons. Now, it turns out because the valence shell for our electrons is related to its position, the element's position on the periodic table, it makes sense that the charge that an atom would gain, either positive or negative, is also going to be related to the group number that is in the main group. Because elements in the same group are going to behave similarly. Same group form ions of similar charge. And here's something to remember. Metals form cations. Okay, metals form cations. For the metals of groups 1, 2, and 3A, the group number equals the charge on the cation. So, group 1A are positive 1s. 2A, positive 2. 3A, positive 3. This is very important to remember, okay? Because this will help you when we're writing symbols and writing formulas. It's also going to help you when we start naming, nomenclature, okay? Naming is a very important thing in this, in these next few chapters because it's a safety issue. Now, nonmetals form anions, okay? For nonmetals in groups 6A and 7A, the charge on that anion is going to be 8, our octet, minus the group number with a negative charge. So, 8 minus 6 equals a negative 2 for the charge. Remember, this is a negative. Another way that you can write this, and the way that I prefer it, is the charge equals group number minus 8. That way you always get your negative sign. It's the same thing as long as you remember that anions are negative, cations are positive. So group 1A, why do they form a +1? Because they only have 1 valence electron. Group 2A has 2 valence electrons. Group 3A has 3 valence electrons. And you might ask, well, why not group 4A, 5A, 6A, 7A? Why don't I lose those? Well, you could, but they're not stable. It turns out that once you start going into the nonmetal territory, it is more stable for the atoms to gain electrons than it is to lose electrons. So for group 6A, it has 6 valence electrons. There are these 2 open spots. If it gains those 2 electrons, now it has a total of 8 valence electrons and a negative 2 charge. Group 7's got that 1 lonely valence opening, so it can gain an electron. Now, group 5A, the nonmetals in group 5A, which are only nitrogen and phosphorus, tend to form -3s. 4A will not worry about, at least not until you get to organic chemistry. That's all about the chemistry of carbon. So, you need to know these. For group 1A, the group 2A, the group 3A metals. Now, they only show aluminum here, but gallium and indium as well form plus 3s. And then our 5A is a -3, 6A -2, 7A -1. Now, why do we have to know the ones that only form a single charge? Because then any other ones that we run into are capable of forming multiple charges. So you'll see here, these guys in the center here, these are metals with variable charge. Now, I'm going to disagree with your book for a second and say that these guys that are outlined in red, silver, zinc, cadmium, we're only going to memorize the one charge. Okay? So silver is a +1, zinc is a +2, and cadmium is a +2. Okay? But all of the other metals here, the transition metals, can form multiple charges. Now, the way we determine what multiple charge we are formed is going to depend upon what our anion is. So we have to know our anion charges as well. Now, without ions, we wouldn't be here, because ions are charged particles. The movement of charge is electricity, and since human beings are essentially large electrified water bags that are capable of movement, thought, and all these good things, we need to have some way for that electricity to move. So ions are part of that. Sodium and potassium in particular are the ones we use for our electrical impulses for the most part, as is magnesium and calcium, which is found in bone and teeth, and also an integral portion of your electrical system for your heart. Iron is in hemoglobin, and chloride pretty much balances out everything else. For any ionic compound, the sum of all the charges in the compound must be 0. There is no such thing as having extra positive or negative charge. So, what we see here, sodium is a +1, chloride's a -1. If I were to go through and actually look at this crystal here, you would see that for every +1, there's a -1. -1, +1, -1, +1, -1, +1. So following this principle, if I have a calcium ion, which is a +2, it's got 20 protons and 18 electrons, and I wanted to have the fluoride ion attached to this, which has only got a -1 charge, that's 9 protons and 10 electrons. If I only had the one fluoride, or one fluorine ion, then I would have an excess of positive charge if these guys came together. So I need a second fluoride to attach to that calcium. So the formula would be CaF2 with a subscript 2 telling us we've got 2 fluorides. Now if you take a look at this picture here, if we were to actually go through, we would see that for every 2+, we've got 2 minuses. Okay? So the principle of electroneutrality. Ionic compounds, the sum of all the ion charges must be 0. So how do we write a formula for an ionic compound? First thing we have to do is figure out which is our cation and which is the anion. Remember that metals are going to form cations and nonmetals form anions. And starting off, we're going to use the group number for the main group element to determine their charge. So KCl, potassium is a group 1, so it's a +1. Chloride is a group 7, so that's a -1. Or calcium, which is a group 2 metal, which is a +2. Oxygen is a group 6 nonmetal, which is a -2. Now, we need to determine how many of each of these ion types do we need so that there's no extra charge. If I've got a +1 and a -1, +1 or 1 plus a -1, so another way to think of this, equals 0. So 1 of each charge. Now if I've got a 2+ and a -2, so 2 plus a -2 equals 0. So 1 of each of these. So the formulas are KCl and CaO respectively. 1 of each of these ions is needed to balance the charge. What if I had the calcium and the chloride ion. Well, that's a +2 plus a -1. +2 plus -1 gives me a +1. That's still extra charge. I need to get rid of that extra charge. So I do so by bringing a second chloride. So if I do that, I have +2, plus now I've got 2 total negatives. So my formula would be CaCl2. Another way you can think of this is by taking a look at the charges up top, a 2- and a 1-. The 2- here means that 2 negative ones are needed. A 1- means that only a 1 of a different cation would be needed. So 1 calcium 2+ ion is needed. Or Ca2 plus Cl-, 2 total calcium or 2 total chlorides for the calcium. We don't need a subscript to show that there's only one of each of these present. Okay? Whenever you have an understood 1, we don't write that explicitly. So it's actually wrong to write C1, Cl1. We only have to do that when we start actually increasing the number of those ions. Now I'm going to go through the nomenclature or naming of ionic compounds rather quickly in this portion. It is more important for you to actually watch the videos that I've supplementally posted online that delve into this in more depth. Okay, so main group cations. So naming main group ionic compounds. The cations are named for the element which they came from. Okay, so the sodium ion is just named sodium because Na is sodium. Ca2+ would be just the calcium cation. Okay, so we just named the cation as its element name. Other cations can be named in a couple of different ways. Okay, and this is what I'm going to talk about in those supplementary lectures. There is a systematic name, okay, which uses Roman numerals in parentheses to tell what the charge of the cation is. So this, when it says other cations, this is when we're having the cations that can form multiple charge, multiple types. In other words, not the ones we memorized. Okay, which ones were those? Group 1A, Group 2A, Group 3A, silver, which was a +1, zinc, which was a +2, and cadmium, which is a +2. These are the only ones that form one type of cation. All the rest of them can form multiple types. So, for example, if I have an iron cation, if it's a +2, that's going to have different chemical properties than if it's a +3 iron cation. We name the cation using the element name iron, but we tell the charge in Roman numerals. This is because it's a +2 charge. This is because it's a +3 charge. We also have the common name, which I really hate to do to you, but it is still used often in medicine. We use the suffix us and ic. Okay? Us is for the lower charge, and ic is for the higher charge. So ferrous equals iron 2. Ferric equals iron 3. I really hate to do that to you. I don't like it myself. It's better to just use the 2 and 3. But those pesky doctors still like to use the ic and the us. You can see this if you take a look at supplements, vitamins in the vitamin aisle. You'll see ferrous sulfate as the iron supplement. So it is still used. I don't prefer it myself, but there you go. So here is a table for those common names. Chromium, chromos versus chromic, cuprous, cupric, ferrous, ferric, mercurous, mercuric, stannous, stannic. These are just the kind of things that you would have to know in order to use these correctly. Now, naming anions, particularly monatomic anions, monatomic meaning only one atom, the way we name those is we take the element name, the root of that, and we get rid of the end and we add IDE. So bromine becomes bromide, chlorine, chloride, fluorine, fluoride, nitrogen, nitride, oxygen, oxide, phosphorus, phosphide, sulfur, sulfide. So monatomic anions just get the IDE ending. So if we're naming those main group, or those ones that only form one type of cation, then we name the cation and then the anion. We do not specify the charge. That is only for when we have those variable charge cations, those transition metals usually. Do not specify how many of these that you have, okay? You don't need to do that. So for naming, all you have to do is just say what it is, because we know, or we should know, what the charge on that cation is. We should know what the charge on that anion is because we've memorized it. So if I put Na and F together, NaF is called sodium fluoride. Mg2 plus and Cl minus to make MgCl2 is just magnesium chloride. Now, if you have variable charge, something like CuCl2, determine the cation charge, and the way we do this is we got to know the anion charge. So I've got 2 chlorides here, 2 chloride anions. That's a total of -2. That means that that cation, that copper, must have a positive 2 charge. Because remember, we have to have a sum of 0 charge. So we name the cation and we name the anion. Now, the systematic way is we name that cation and we give it its middle name, its Roman numeral, telling us, remember, this is the charge of the cation. Not the number of them, just the charge. So copper 2, and then we name the anion chloride. Copper 2 chloride. If we were to use the common name that we use, this is the larger of the two, so this is the ic, so this would be cupric chloride. Both names are acceptable, copper 2 chloride or cupric chloride. Hopefully, one day, that will be the only name that we use. So let's write the formula for tin 4 oxide. Tin 4, this 4 is telling me the charge on the cation. In other words, this is tin with a 4 plus. Now the oxide comes from oxygen. It's in group 6A, so this is going to take a -2 charge. So I've got tin with a 4 plus, oxygen with a -2. How many of the tin and how many of the oxygen do I need so that I have no net charge? Well, if I have 2 of these guys, 2 negative and 2 negative is 4 negative, and a 4 plus, so SnO2, tin 4 oxide. So remember, you need to determine the number of those anions present in order to balance the charge on the cation. Now, physical properties of ionic compounds. Ionic compounds are usually crystalline solids. Okay, they form beautiful crystals. Take a look at salt under a magnifying glass. It's actually quite gorgeous. They have high melting and high boiling points. When was the last time you melted salt on your stove? That's right, you never have, because they melt at a very, very high temperature. Now, any ionic compound that dissolves in water does something very amazing. It separates out completely into its separate cations and anions. So sodium chloride in water, I get the chloride ion and the sodium ion. They're separate. They're free to move about. What this does is this allows for electrical conductivity in the solution. Solutions of ionic compounds that are soluble in water are going to allow electricity to flow through them. We call these, just a preview, electrolytes. So when somebody says, hey, it's got electrolytes, it's got what's good for you. No, it's just salt. Okay, it's just some sort of salt. And by the way, the term salt is just generic for an ionic compound that dissolves in water. Now, dealing with monatomic anions and cations is pretty simple, okay? However, it's not very exciting because there's a lot more stuff in this world than what we see just with monatomic ionic compounds. What we have are polyatomic ions. Polyatomic ions are cations or anions that contain more than one atom. So, for example, CO3 2-. These guys behave as one unit. This is one ion. So, when we were drawing ions before, we had just like the sodium ion and the chloride ion. This is going to behave much the same way as the chloride ion. It's just going to be its own unit. So if I have the sodium ion and the carbonate ion, okay, this one's a plus, this is a 2-. I'm going to need 2 sodiums for every 1 carbonate. So the formula would be Na2CO3. So there are a lot of common polyatomic ions that you should be familiar with. Especially know these ones in bold very well because they're going to come up. And this one also you should know, HCO3-, the hydrogen carbonate or the bicarbonate ion. Very important ions to know. Why? Well, if we know, or if we're trying to do nomenclature of one of those multiple cation species, we always have to know the anion and the anion charge. So, when we write the formulas for the polyatomics, the cations and the anions need equal charge to combine. So, if I've got a sodium plus and a nitrate minus, I need to know that the nitrate is a -1, so that when I have NaNO2, I know that that is completely charge balanced. Similarly, if I've got barium, I need to know that the sulfate is a -2, because I need to know that in BaSO4, that is charge balanced. Now, if they're unequal charges, then we have to do something special. So, when you have unequal charges, we need to use parentheses to show that I've got 2 of these OH units. OH minus means that I've got the hydroxide. It's one whole unit. OH in parentheses 2 means I've got 2 of those units. I need 2 of those to balance that Mg2 plus charge. Now, the same rules for naming our ionic compounds work with these polyatomics. So, for these guys are the main group. For the main group, we name the cation and then the ion. We don't specify the charges. We don't tell how many of them there are. So NaHCO3 is simply sodium bicarbonate or sodium hydrogen carbonate. Al2SO4 taken 3 times is aluminum sulfate. Okay? As I said, watch the videos on nomenclature especially. I think this is probably the hardest portion of this chapter. And work as many example problems as you can. Work problems from the back of the book as well. Additionally, your lab book in the study aids, and there's worksheets, okay? If you work on those and you come in on Thursday, I would be more than happy to go over them and take a look and see how you're doing with nomenclature. So, until next time.